Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at monotonic continuous functions, and this will be mostly just an application of the intermediate value theorem. And we looked at some applications last time. Basically what we saw was a fixed point theorem, which said that if you have a function from a closed interval to the same closed interval, which is continuous, then, not just any closed interval, but this guy, 0, 1, then such a function has a fixed point, meaning there is an x sitting inside this closed interval such that fx equals x. So we saw that, and we saw that any odd degree real polynomial has a real root, meaning it vanishes at some real number. And lastly, we saw that this particular function is a bijection from this to that. If n is odd, then in fact it's a bijection from all reals to all reals, but if n is even, then we can say only this much. And this is what one can use to show that square roots, or rather just any nth root, it exists provided you feed a positive number to it. When you have odd exponent, then you can feed any real number to it, but for even exponents you can only feed non-negative reals. So we saw all of that, and now let us go to the problems. These are the problems, and now let us look at the definitions that we need. So we defined the notion of monotonic sequences previously, but now let us define more general notion of a monotonic function. So let f s to r be a function. So we say that f is increasing if f of x is less than equal to f of y whenever x is less than equal to y, for of course x and y in S. Otherwise this does not even make sense. So this is the definition of an increasing function. Now we define strictly increasing. We say f is strictly increasing if fx is less than f of y whenever x is less than y. Again, x and y in S. And similarly we define a decreasing function and strictly decreasing function. So these two terms one can define for oneself, and we say that f is monotone if f is either increasing or decreasing, and strictly monotone if we know what happens. So we define these two terms. So it's monotone if it's either increasing or decreasing. It is strictly monotone if it's either strictly increasing or strictly decreasing. So some obvious definitions. Alright, and now let us see maybe one or two examples. So the first example is the function which takes x to x square. This is not monotone. This is not monotone simply because if you see the graph of it, it looks like this. And it is decreasing on this part, but it is increasing on this part. So as you can see that it is not increasing or decreasing on the entire real line. Here it is decreasing, but then it increases. So there. This is not a monotone function, but let us see another example where it is actually a monotone function. We take all positive reals and then we map into reals via this rule. This is strictly decreasing. As we know, one can see this using the graph, but of course one can prove it formally if really needed. So this is how it looks, and therefore it is a strictly decreasing function. It keeps on decreasing. Alright. And now let us look at some very simple facts about monotonic continuous functions, or rather, well, I shouldn't say monotonic continuous functions, so we'll see what I want to say. So here is a lemma. So let f be a continuous function on this closed interval. So we have continuous, and if we assume injectivity, if f is injective, then f is strictly monotone. So I'll give a proof, but not all the details. But I think it will be clear what the proof is. One can easily write down one's own proof. So assume fa is less than fb. Why can we assume that? There are three possibilities: either fa equals fb, or this, or that. If fa equals fb, then injectivity would be contradicted, so that case simply cannot arise. So there are two cases. We'll just argue for this case, because the other case is perfectly symmetrical. So we'll assume this, and then we'll show that. We will show that if x and y are in this closed interval with a less than x less than y less than b, then f of a less than f of x less than f of y less than f of b. And if we show this, then we are done. Then it would prove that the function is strictly monotone. So first let us argue that f of a is less than f of x. And let me not write anything down, I'll just show it via a picture. So let's say this is a, and this is b, and let's say this is fa, and that is fb. So when I write fa here, what I really mean is that this length is fa and this length is fb. Alright, and x is, let's say, somewhere here. And we want to argue that f of x exceeds fa, so it is not equal to that, and it is not even below that. So, well, why is it not equal to fa? Because if f of x were equal to fa, then the function wouldn't be injective, because it is taking the same value at two different points. So if this is not true, the only other possibility is that f of x is somewhere here or here. I mean, it's below this horizontal line. So let me just let me shift this a little bit upstairs, because we are not able to see otherwise. So let's say this is what fx is. It is strictly below f of a. So then the function kind of goes like this, and intuitively what happens is that if we draw this horizontal line, then the function must cut this horizontal line somewhere here. Which would mean that function is not injective, because it would take the value fa at the point a as well as the point greater than a. So that would contradict the injectivity of the function. How do we argue that? How do we make this argument precise? We use the intermediate value theorem. One way to say is that the function takes a value less than f of a at some point and greater than f of a at another point, then it should take the value precisely equal to fa at some point in between the two things, because it is a continuous function. Or you can also use the other formulation, is that the image of any interval under a continuous function is again an interval. So if you take the image of this interval under the function f, then you'll get an interval which contains this value, this number and that number. So it contains all the numbers in between, because it is an interval after all. And one such number is between is fa. So it should take the value fa somewhere here, and that's it. This contradicts the injectivity of the function, so we have argued this. In fact, similarly, one can argue that it's exactly the same argument. And finally, we will argue this. Again, I'll just draw a picture and show you. So in fact, the picture is already here. So let's say this is y, and we have already shown that f of x is somewhere here. It cannot be less than fa. And f of y is, let's say, it is less than b, and we also know that it is also not less than f of a by the same argument. So both f of x and f of y are between these two horizontal lines, and for the sake of a contradiction, let us say that f of y is less than f of x. F of y is somewhere here, let's say. So we want to give a contradiction, and again it's the same thing. If you just look at the function in this interval, then what it is saying is that since f of y is exceeding f of a and it is less than f of x, if you draw this horizontal line, it will cut the graph somewhere here, meaning there is a point between a and x where the function takes the same value as f of y, and that will contradict the injectivity of the function. So it's basically the same argument done 2-3 times in this proof. I believe one can do it more efficiently, but anyway. So just convince yourself that this holds, and now we generalize this as a corollary. Immediately as a consequence of the above lemma, we have the corollary that let f be a continuous function where I is an interval. So we are not assuming that I is a closed interval of or anything. It's just some interval. If f is injective, then f is monotone. F is strictly monotone. Okay. So it's a clear generalization of the previous lemma. And here is how we'll do it. So let a and b, a comma b, I shouldn't use these notations, but anyway, so let a comma b in I be such that a is less than b. So we have just picked 2 points in the interval, and again there are only 2 cases: either fa is less than fb or fa is greater than fb, because equality cannot hold by injectivity. So assume fa is less than fb. The other case is perfectly symmetrical. Alright, and then so we'll show that the function is actually strictly increasing. And let me again just draw a picture. So here is where we have a, and here is where we have b. Okay, and now just immediately by the previous lemma, we know that the function is strictly increasing on this closed interval, because a comma b is after a closed interval where the function is function takes this, behaves in this fashion, which is precisely the hypothesis, and that allows us to deduce that f is strictly increasing by the previous lemma. So it is strictly increasing in this interval, and now if c is any other point, let's say c could be here, c could either be here or there. I don't know how the interval I looks like, but it is some interval. So let's say we pick c somewhere here. Here is where c is. Then there are 2 possibilities. Either the function on this interval is strictly increasing, but then it is strictly increasing in this entire interval, or it is strictly decreasing in this interval, again by the previous lemma. But since it is already strictly increasing here, it cannot be strictly decreasing in this part, because we also know that it is strictly monotone in this interval, right? Because this is also a closed interval in the domain, contained in the domain of f. So it is strictly monotone here, and by this assumption it is strictly increasing here. So it is strictly increasing through and through. So what this shows is that what this argument, which I did not really write down, but what I've argued is this. So if we pick a point which is on the right side of B, we have that. And similarly, if we pick a point on the left side, let me call this maybe, I don't know, P, let's say. If we pick a point on the left side of A, then it will satisfy Fp less than that. So by the similar kind of argument, because the function is strictly monotone on this interval, and it is strictly increasing on this interval, so it follows that this should be the case. And basically what we have shown is that if you pick any 2 points in the interval I, let's say x and y, with x less than y, then f of x is less than f of y. Because you can just make multiple cases and argue. So either x is here and y is there, or x is here and y is here, but just in every case you can argue that f of x is less than f of y, so f is strictly increasing. So under this assumption, we end up showing that f is strictly increasing. Under the reverse assumption, we'll end up showing that f is strictly decreasing, and so on. This is not a difficult argument, and you can fill all the details. So that's it. And let me check if there is anything else. No, that's it. So this is all that I wanted to cover. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.